Welcome to section 9.2.3. We're going to be talking more about complex numbers and equations. Now, in order for us to graph a complex number, we have to use what's called the imaginary plane. Now, what we're doing for the imaginary plane is we're replacing the x-axis with the real axis, and the y-axis is our imaginary axis. Now, you kind of want to think about imaginary numbers that they exist. They're just existing in a different dimension than we're used to seeing. And that's what it is. Imaginary numbers do exist, but they exist in a different dimension. When we write an imaginary number, it's written as a plus bi. And a is the real part, and the bi, that's our complex part, our imaginary part. So the a is basically our x-coordinate, and the b is basically our y-coordinate. So when we go to graph these, 2 plus 5i, we go over 2 in the real and up 5 in the imaginary. That's where 2 plus 5i is located. For 3 minus I, we go over 3 in the real and down 1i in the imaginary. 3 minus I is there. Negative 5 minus 3i, we're going back 5 and then down 3. That's where negative 5 minus 3i is located. 4, there's only the real part, so we're just going to go over 4 in the real, and that's our answer. For 3i, we're going to go up 3 in the imaginary. And then for negative 4 plus 2i, the real, we're going back 4, and then we're going up 2 in the imaginary. And there is our numbers plotted on that complex plane. Make sure when you graph these that you're labeling your points as well as I did. That way you know exactly where the points are located and which points you're graphing. Now we're going to graph the following and find the absolute value. So 3 plus 4i, for the real we're going to go over 3 and then up 4 in the imaginary. Now, to find the absolute value is the distance away from 0. Now, when we're on this imaginary plane, we're finding the distance not from just 0, but the distance from 0, 0, the origin. So the distance is this diagonal line. Now, what we could do to find the length of that diagonal is, since we can't count a diagonal in the coordinate plane, or the imaginary plane, is we're going to drop a vertical and a horizontal and draw a right triangle. So this horizontal distance is 3, and this vertical distance is 4. And what we could do to find the absolute value of 3 plus 4i is use the Pythagorean theorem. A squared plus b squared equals c squared. We're looking for that hypotenuse. 3 squared plus 4 squared equals c squared. Notice I'm not including I. I'm just looking at the values. 9 plus 16 equals c squared. 25 equals c squared. Take the square to both sides, so c equals. Now, it's the distance, so we're only looking at the positive square root, so that's why c is 5. So the absolute value of 3 plus 4i is 5. That was the absolute value. That's the distance from the origin. Now for negative 2 minus 3, we're going to go back 2 in the real and down 3 in the imaginary. So once again, draw a horizontal and a vertical to make a triangle. This distance here, we're going back 2, negative 2, and we're going down 3. That's a negative 3. And we're finding the hypotenuse. That's the distance. A squared plus b squared equals c squared. Pythagorean theorem. Negative 2 squared plus negative 3 squared equals c squared. When we square that negative, we're going to get a positive, so it's going to be 4 plus 9 equals c squared. 13 equals c squared. So when we take the square root, remember, we're only looking at the positive square root, which in this case is the square root of 13. So the absolute value of negative 2 minus 3i is the square root of 13. And it all comes from that Pythagorean theorem, because the absolute value is the distance from the origin. Now, here, instead of having to draw the triangle every single time, the absolute value of a plus bi is z. And that's the distance between the point and the origin. So the absolute value of negative 8 plus 6i is z. So z is going to equal the square root of a squared plus b squared. And that's just the coefficients. For a, that's our negative 8. It's in that form of a plus bi. So it's going to be negative 8 squared. B is what's in front of the I. In this case, it's just going to be a 6. Negative 8 squared is 64. 6 squared is 36. You get the square root of 100. And that's going to be 10. So the absolute value of negative 8 plus 6i is 10. The absolute value of 7 minus 2i is going to be our z. And that's just going to be the square root of a squared plus b squared. A is our 7 and b is our negative 2. Square root of 7 squared plus negative 2 squared. 49 plus 4, the square root of 53. So the absolute value of 7 minus 2i equals the square root of 53. It can't be simplified. And then the last one, the absolute value of 4 plus i is z. So it's going to be the square root of a squared plus b squared. So for this one, this a is 4. And b, in front of the I is just a 1. So it's going to be 4 squared plus 1 squared. So it's 16 plus 1. So you get the square root of 17. So the absolute value of 4 plus I is the square root of 17. Remember, we're only looking at the positive square roots and not the negative, because distance is always a positive number. Now, as we talked about with the discriminant, we can find the number and type of solutions, the number of roots, and such by looking at the x-intercepts. Now, there's one turning point, so the degree here is going to be 2. And now, because there's 2 x-intercepts, that means there's 2 real solutions. Number 13, there's 2 turning points, so our degree is going to be 3. And we can see so that means there's going to be 2 solutions here. So there's going to be there's 3 x-intercepts. So since we have 3 x-intercepts, we have 3 real solutions. For number 4, our degree is 2. So we should have 2 solutions, but there's no x-intercepts. Since there's no x-intercepts, that means there's no real solutions. That means there has to be 2 complex solutions or 2 imaginary solutions. Now, number 15. There's 2 turning points, so our degree, we'd add 1 to it. Degree has to be 3. Now, that means there needs to be 3 total solutions. But I only see 1 x-intercept. So if that's the case, that means there's one real solution for our x-intercept, and that means there's also going to be two complex solutions. There's going to be two imaginary solutions. And that's because we need to add up to 3. One real, two complex, total of 3. All right, let's go to the next page, please. Sketch a third-degree polynomial that would intersect the x-axis at 1, 2, or 3 times. So remember, third-degree polynomial, it's going to have 2 turning points. So it's going to look like this or like this. It doesn't matter if you have a positive leading coefficient or a negative leading coefficient. So for A, one x-intercept. So one real solution. So it could look something like that. It's got 2 turning points, but it only crosses the x-axis once. For B, 2. So to have 2 zeros, two x-intercepts, so it would have to go up, back down, and then it would bounce. Now that would be 3 real solutions. So that would be 1 real for the first one, and then 2 complex. This would actually be 3 real solutions with a repeated solution. So for a total of 3, but one of them is being repeated. And then for part C, where it intersects 3 times, we'd need 3 separate x-intercepts. So that would be 3 distinct, and once again, 3 real solutions. Now, could any of them have 0 real roots? And no, it's not possible to have 0 real roots. So no x-intercepts is not possible because of the shape. Because of the shape of it, it's always got to go through at least once. So our only actual options for real zeros is 2 or none. We can only have 2 complex solutions or no complex solutions on that one. Now, consider the graph. How many real solutions could the function have? Well, the degree is 3, so it could have 3 real solutions. Now, if we graph this on the calculator, it actually has 1 real solution, and the other 2 are complex. And if you look at the sketch of the graph, you'll see that. Now, we're going to verify that these 2 equations are equal. So what we can do is we can distribute the x and the negative 2, so we get x cubed minus x squared plus x minus 2x squared plus 2x minus 2. So we combine, we get x cubed minus 3x squared plus 3x minus 2. And you can see those are equal. So they're equivalent. Now, what that equation on the left-hand side comes from is that was begun to be factored. And that's what we're going to get into in the next part of the chapter. This is factored form. So if we're going to find the solutions, we actually can't factor this any further. So to find the solutions, we would set x minus 2 and x squared minus x plus 1 equal to 0. Now that it's in factored form to solve, set each factor equal to 0. So we get x equals 2 for one of our solutions and an x squared minus x plus 1. When we set that equal to 0, it can't be factored. So what you would use is the quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. So the opposite of negative 1 is 1 plus or minus the square root of negative 1 squared minus 4 times 1, all divided by 2 times 1. So x equals 1 plus or minus 1 squared is 1 minus 4. You're going to get the square root of negative 3 under the radical over 2. Now, the square root of negative 3, that simplifies to become the square root of negative 1 and the square root of 3. So that's I root 3. So it equals 1 plus or minus I root 3, all divided by 2. So what we'd do is we'd split that up. So x equals 1/2 plus or minus I root 3, all divided by 2. So there's our three solutions. X equals 2 and x equals 1/2 plus I root 3 over 2, x equals 1/2 minus I root 3 over 2. There's our three solutions. And as we saw in the graph, there was only one x-intercept. And if you look at the graph again, that x-intercept is at x equals 2. And that's going to be what we're going to be talking about in the next section, about solving these polynomials with the help of our graph. Okay, thank you, and I will see you in the next part.